I will talk about one of my passions, which is trying to understand how solid catalysts, heterogeneous catalysts work. And for this, we use tools, not only X-rays, but I will limit myself today to X-rays and how you can apply them to have them studying solid catalysts while they are in action. So for those who are not so familiar with the field of heterogeneous catalysis, I think it's a real example of multi-scale science. Multi-scale in the sense that it crosses different length scales going from atoms, molecules, so angstrom nanometers, over micrometers to millimeters with catalyst particles and bodies up to meters when you have a real full-fledged industrial reactor. And just to show some of these shaped catalyst particles, I show them here on the left. You can see that they are microscopic bodies. You can see them with your eyes. But if you want to really study them in great detail, you will need spectroscopy and microscopy. What is the mission? The mission is actually to turn our society in one which is more sustainable, more circular, and it means that we will gradually shift our energy and materials mix from one which is currently dominated by fossil to one which will gradually use more and more waste, biomass, but also solar. And that will require technological breakthroughs. For these technological breakthroughs, we will need science and technology. Amongst others, it will involve catalysis. Here I put for you as a kind of, just a visual, the refinery of the future, but nobody knows exactly what it will be. It will contain different things, but for sure it will require a lot of energy if you want to replace the fossil resources which are currently using. And today I will focus on small molecule activation, more specifically CO and CO2. I already mentioned about the passion which I share with all the groups is that I would like to use spectroscopy and microscopy in such a manner that we literally shine light in a reactor while it's operating, providing spectroscopic data, but also online activity selectivity, and try then to correlate them by then shedding insight on structure and composition. This so-called Operando approach is now, I think, really established in the field, and many of us are trying to push that further, step by step, towards an ambition, which at least I have, is can we somehow go into what I call a catalysis movie studio, light, camera, action? Can you have here your cameraman, and while this is happening, you want to do this? That means that you want to do that in a space and time resolved manner. Space means that you have to zoom in and zoom out. All length scales are important, and time means that you want to have short and long periods, and also you want to have pulse experimentation. By doing this, you want to capture what we call spatiotemporal dynamics. Why is it now so important? Actually, what you want to do is you want to understand and tailor the active site. Now, the active site is a concept which is around already for years and has been coined in the heterogeneous catalysis literature, at least by Tailor. And he was already aware that it is often only a small fraction of atoms which are somehow dominating the game. And based on that, there are now two schools of thought, and they have been developed partially by having surface science methods, Ertel Somogyi as two very much prominent people in that field, but also by trying to develop operando techniques and transient matches and single molecule and single atom methods. So here I show you the Langmuir school of thought, where you have facets which are then studied in great detail, or you have the Tailor approach, where you see that you have actually some atoms which are actually dominating the game, and therefore you want to have single molecule, single atom, and transient methods to decipher what is going on. I put forward two recommended papers to read. I have one to share which just appeared in Nature Reviews Chemistry, where we allude on the concept of active site and how you can elucidate it with spectroscopy and microscopy. And the other one which I want to bring under your attention is one where you see what the field is all about. You want to explore space, time, and action. You want to have a camera where you have this film. And what you also see is that you combine techniques. You want to go to more realistic conditions. You want to have a better time resolution going faster, but you also have to realize that you want to go longer, because catalysis is a process which requires not just seconds, but all over actually. A process will take not only days, months, but often a catalyst is put into a system for years. And here I show you this other recommended reading, which is a Nature Reviews material review, which we wrote. But I also recommend this special issue, which is devoted to synchronotron radiation. That brings me to the theme of the topic of today. I want to talk about catalytic hydrogenation of CO, CO2 with hydrogen. And I will focus on these four elements: cobalt, nickel, iron, and a little bit copper. And I have divided and also made some breaks, as Jerry has also suggested to do that, where I will talk about quick XAS, scanning transmission X-ray microscopy, then we have a break, transmission hard X-ray microscopy, long duration experimentation, lab-based X-ray diffraction, then a break, lab-based X-ray absorption spectroscopy, and then we have final discussions. So let's first start with one reaction which I want to explain is the Sabatier reaction. And the technique which I want to explain is quick XAS. And the topic I want to discuss is structure sensitivity and metal nanoparticle restructuring. The reaction is CO2 hydrogenation. Here I show you a plant which you can find actually in World Germany, not so far from the Dutch borderline, where you have a small pilot scale plant where they hydrogenate CO2 with hydrogen to methane. We have been building in the lab this setup by using solar panels, which provides electricity and electrolyzing, making hydrogen, capturing CO2, and then converting it to hydrocarbons in this setup. I will not dwell today with electrocatalysis. I will focus on thermocatalysis. Now, in practice, I already stated that it's a multi-scale science. This is the reactor. These are the X-rays. You zoom in the pores. You have metal nanoparticle, and here you see a single metal nanoparticle which is in place and is doing the job. This metal nanoparticle is not just a metal nanoparticle, but has facets, has certain rounds, kinks, and whatever. And the question is, who is doing what here? What is the active site? Can we somehow titrate this surface with CO2 and make methane? For this, we have been studying a wide variety of nickel silica catalysts, nickel nanoparticles, which differ in their metal nanoparticle dimensions. And by doing so, we can change the activity by changing the nanoparticle. Here I show you CO2 molecules converted per nickel surface. And we can do that for CO2 hydrogenation or ethane hydrogenation. If you see CO2 hydrogenation, it has a maximum. And with ethylene hydrogenation, it has not. We call this structure sensitive. We call this structure insensitive. And somehow you have a maximum around 2, 3. So here somehow facets are dominating. Here seemingly facets are not dominating. Can we elucidate this? The first technique which I want to discuss with you is Operando quick X-ray absorption spectroscopy. I want to discuss experiments which have been done at a Swiss light source. Swiss light source has a beam which allows actually to do transient experimentation, quick mode, quick XAS mode. And what you can do is you can bring in, or your operando cell in transmission in a capillary, and then study in detail what is going on in the catalyst. We have online activity measurements to guarantee that indeed catalysis is going on. In other words, it's operando mode. Let's first see what happens during the reduction in hydrogen. This is fresh, this is reduced, and here I show you the different metal nanoparticle sizes of nickel on a silica support. All of them reduced to the metallic state. Now, more interesting is what happens during CO2 hydrogenation. So what we did is we actually have been measuring the changes happening during this process. What you also have been doing is we have been making pulses of hydrogen, CO2, hydrogen, CO2. Now, important is that you can now do a cluster analysis. I come later on to that. And you can also measure the nickel metal and the nickel oxide references. You can see then how it changes from the metal to nickel oxide and relative its contributions of these different species of metal and metal oxide species. If you do this and you give short pulses of hydrogen, nitrogen, CO2, the system actually somehow responds to these pulses. What you can notice that if you put metal percentage as function of these pulses, you can see that actually you change when you have hydrogen more metallic, and when you have the CO2 somehow, then there is an adsorbed CO2 on it, hence the surface has some oxygen at its first surface. Now, this works very well for small nanoparticles. With larger ones, you see that you have some bumpy road here. Nevertheless, what you can do is now compare these structure sensitive with structure insensitive reactions for 400 with CO2 and hydrogen, or with ethylene and hydrogen. Should not be an expert to see that here the differences are less than here. But in any case, somehow restructure is going on, and this restructuring is nanoparticle dependent. You can see clearly that these differences are not exactly the same for each metal nanoparticle. So this already indicates that there is metal nanoparticle restructure, and it is size dependent and reaction dependent. Can you now, by focusing on certain energies, see what is happening? And here I show you two energies which are representative, and I show you this as function of the metal nanoparticle. We actually blow up the changes by having here this normalized. But in any case, you can see that there are changes, and the changes are the most active particles restructure the most during CO2 hydrogenation. And in the case of ethylene, the larger particles restructure more. Now, to focus more in this, we can also plot it as R in R space. And here I show you the reduced in hydrogen ethylene, and see how it responds actually. So here you see the nickel-nickel bond, and here you see the nickel-nickel multiple scattering. And here I show you the different pulses which are giving hydrogen, CO2, or hydrogen, ethylene, in this case, ethylene. So here you can show, if we show that actually the nickel-carbon bonded phase dynamically distorts, and we believe that it dynamically distorts also the catalyst particle. So this was my first part on CO2 hydrogenation and transient experimentation. Now I want to move to another process, which is Fischer-Tropsch. The previous Sabatier was CO2 hydrogenation. Fischer-Tropsch is CO hydrogenation. It's a process which is already known for, let's say, 100 years, invented by these two gentlemen, Fischer and Tropsch, and they initially used iron. Now, since then, this has developed to technology which is not only practiced in, for example, South Africa, but also at different places on Earth, for example, in Qatar, where there is a Shell plant. Shell Pearl operates with a cobalt-based catalyst, cobalt titania catalyst. You can use different resources for carbon, and you can make, for example, then synthesis gas, CO hydrogen, lead it off this bed, then you make long hydrocarbons, which you crack and make, for example, gasoline, diesel, and so on. Now, what is now of importance here? Do we have a metal as cobalt? Do we have a cobalt oxide? Do we have it as a carbide? Is a carbon deposition happening, and so on? Can we somehow decipher or obtain information on these different states of cobalt during a reaction? And the first technique which I want to discuss before we have a first break is Operando soft X-ray microscopy, of Operando scanning transmission X-ray microscopy. I show you today results of the advanced light source, but we are doing that at different light sources all over the place. We have been using or developing that over the years. Already in 2008, we published on this. And we have been gradually trying to make it from in situ up to really Operando. Today, I will only discuss the truly Operando. And that also means we have been discussing or developing different cells to make that possible. The advantage of soft X-rays is that you can measure a kind of XPS spectrum. Hence, you can measure low and high Z elements together. So that means you can measure of a cobalt titania catalyst while CO is hydrogenated. You can not only measure the titania and the cobalt via the spectrum, but also the carbon. So you can measure organic and inorganic while the reaction is happening. The reaction happening we determined by online mass spec. We had an in situ cell to do that, which was actually a spiral system where the catalyst particle was in between these spirals of platinum. And that allowed transmission X-rays in, X-rays out. And when the cell is thin enough, you can do this. So back to this cobalt titania catalyst. You have references, cobalt titania, cobalt metal, and you can reduce the catalyst in different ways. You can, for example, see that when you reduce it in a certain way, you measure almost a spectrum, which is cobalt titania. Do you do it in another way? You have mainly cobalt metal. So seemingly this titania, you can really play what we call strong metal support interaction. The titania can creep on the cobalt or just leave the cobalt need for catalysis. Now, depending on this different treatment, and hence different spectra, more cobalt metal, more cobalt titania, you can see that you have also different spectra in the carbon KH. That means you can measure what is happening at the surface of this cobalt nanoparticle. But before showing that, I first want to show you, you can measure cobalt and titania, time resolved, 0, 19 hours, 41, 51, 69, and the same holds for the titania. And you can do that spatial resolve. For example, here I show you principal component analysis, where you see certain spectra depending on a certain, what is it, one catalyst particle. So you see differences in the different metal nanoparticles as function of time. But the carbon spectra are even more interesting. And what I mean by it is that you see here 0.5 up to 65 hours. It's about, let's say, 3 days. This is far from trivial to do 3 days of an experiment where you follow the same particle as function of time in a reactor under pressure and high temperature. Nevertheless, we succeeded. And here I show you the space resolved maps and the time resolved maps. When I focus now on, for example, 0.5 hours in the carbon map, you can see that you have different features. Important is to see here that this aromatic one is low in intensity, and here you see oxygenated, which actually you can also see in the reactor first, and then you also have aliphatic, what you expect. And when time develops, you see this aromatic, and so developing further. I don't have now the time to discuss that, but these are indeed precursors which are put on the surface and are these carbon deposits which are likely formed during the catalysis. So this brings me Jerry, to my first break. And I have now time to discuss the first questions. I will just unlock the screen for.
You should just keep sharing your screen.
Oh, okay.
That's all right.
Yeah, I will bring it in again when I see the questions.
I don't think I'm waiting just to see if anyone puts a question in, but as yet, no questions. I think you should. I think you should continue, and people will hold their questions till the next break.
Good. Then I continue. So feel free. I'm prepared really with breaks. So this is also, I hope that there are students, because I also made it a bit in that manner. Good. Which brings me, after I showed you soft X-rays, let's say 500-600 eV, I want to show you something on hard X-rays. And this also is an approach which we have been developing together with beamline scientists over the years. And the main developments we have been making at SLAC in Menlo Park, California, USA, at beamline 6.2. And here I show you some of the beamline scientists who have been involved in these endeavors. And I also have to have a lot of gratitude to the first postdoc, Ines Gonzalez-Quimes, who has been working on this. Now, it sounds trivial, but I just show you here one of the challenges. Here I show you a very tiny capillary which contains the catalyst particles. And here gases come in and gases go out to a mass spec. And this device is put here. And this rotates. And at the same time gets gases over it. And this is a heater which can be brought down with these screws. That means that by doing this, you can now bring this under pressure, under temperature, and do catalysis. The first thing, I hope the movie shows. I don't know if the movie shows. It has a delay, actually. I hope you see at least in the left corner color changes, and in there it should rotate, actually.
It rotated just a little and then froze on my screen.
Yeah,
but,
I hope it will work. Okay, maybe it will. I will try to see if it works again. Wait. At least it worked on my computer, but okay, I can also do it this way. So now I do it a bit manual, my excuses. You see, what I want to show you is the different components. What I show is an industrial Ruhrchemie catalyst, which was years ago by, for example, already Ruhrchemie, Fischer and Tropsch, was using its synthesized recipe, which we have been making from iron, which contains zinc, green, and this yellowish is titanium. And I show you a particle which we can do in 3D and study in detail. The left one, the left upper image, is actually one where the catalysis is going on, and I show you the changes taking place in the different phases in this iron, zinc, and titanium. Now, this is an example where I show you that we can do 3D operando. I will come back now to the catalyst which I want to discuss in detail, which is the cobalt titanium. Cobalt titanium, here I show you a 2D image. This is the spectrum. We can determine with different compounds what it is. Actually, it's cobalt oxide. Then you bring it in hydrogen, you reduce it. Spectrum changes. I have to admit, it is noisy, but you have already seen this tiny capillary. So I hope you're also convinced this is a challenge to do this. But we succeeded, and we can measure further. 0 hours of catalysis, 10 hours of catalysis, and we have been determining cobalt oxygen, cobalt titanium, cobalt metal. Hardly cobalt oxygen, hardly cobalt titania, although you can say there is some noise in it, so I'm not excluding it, mainly cobalt metal. And that is what also is the hypothesis in the literature. However, as I will show you, cobalt oxygen, cobalt titania, and cobalt carbide can exist. Why I'm saying so? Because now I have to cut a long story short. We did hard X-ray, soft X-ray, which I discussed before, STEM yields, I will not dwell on it. And here I show you fresh and after catalysis. Fresh after catalysis. And that greenish is actually a carbon deposit. And here also you see changes. What is happening? You have a microscale redistribution and a nanoscale distribution, where you have carbons which are depositing. Remember these aromatics which I already shown you before in the Stixum. But also, but that's maybe less obvious from the Stixum, but if I would show you the 3D image, you see also migration. So you see microscale redistribution of cobalt and nanoscale redistribution taking place during catalysis. Now, building further on that, can we now study this under high pressure and really going to good conditions, which are those which you can find in industry close, at least getting closer. So can we go to something like 15 or 20 bar? Here we worked, and I thought I saw Simon there in the audience, and we did that together at Beamline 2.2 Slack. So it has been published in ACS Catalysis. This is the catalyst which I discussed already, 10 or 15 weight% of cobalt, titanium. And the first thing I want to discuss is not the X-ray spectroscopy, but the X-ray diffraction. In our lab at Utrecht University, we have a setup which allows you to do X-ray diffraction in the lab together to Raman, together with UV-Vis. This setup is operando, so you can also measure for this catalyst the conversion. And this should just convince you that you may not make just methane, but also higher hydrocarbons. If this catalyst is now put at the beamline at Slack, and I'm still talking about the X-ray diffraction. If you now analyze the X-ray diffraction and you follow the different diffractograms or peaks, which are typical for carbide, metal, what you see is that you have here the formation of carbide. You can also see that you have another peak, which is somehow increasing, but not that much. But in the beginning, you don't see a lot. And that the cobalt metal phase is actually dropping. What we first did, we reduced it, and then we did catalysis. And here the same. We actually reduced it, and then we did catalysis. This is the X-ray absorption spectroscopy at 16 bar during Fischer-Tropsch. I will discuss the spectra more in detail, but I hope you see that a lot of changes are happening. I already put here two references, cobalt foil and cobalt carbide. And here I show you the start and the end in the radial distribution function for the XAS. And you can really see that the start is much more like this. In the cobalt carbide, at least you see some contributions, but that I will have now to prove to you. So what are the metal and metal carbide phases present during catalysis? And I will show you first the multivariate analysis and cluster analysis. So we did this. We did a principal component analysis on all the data. We clustered them, and we found 5 typical clusters next to the reference. And here I show you that you first have the first component, then the second, then the third. And here I show you the differences in the pre-edge and the white line for these different clusters. What are now these clusters? Well, if you put these clusters and you look into what their contributions are of the different important phases, Here you see hexagonal close backing for cobalt, FCC backing for cobalt, and a carbide. And you gradually see this formation of the carbide and decrease, as I already showed with X-ray diffraction. What about another way? If we do a linear combination of reference compounds, what are the reference compounds? Cobalt oxide, two forms, the HCP, FCC of cobalt, and the cobalt carbide. And here I show you the structures. If you take this, you can do a fitting. And now we did a lot of fittings. And now you have just to believe me that this is then the one which, in our opinion, fitted the best. And what you notice is that cobalt carbide increases as function of time. And then something peculiar happens. Seemingly, the carbide is first consumed at the expense of the FCC cobalt. The HCP cobalt is still around, then somehow, and then drops. So first you consume seemingly the FCC and then the HCP. If you bring now these different results together, X-ray diffraction and XAS, what you see is that you have a gradual buildup of this carbide, a gradual drop of the cobalt FCC, and that you have different contributions of these, and you can measure them both by this cluster approach or by this reference approach. Important is that the carbide formation does not correlate with activity. In other words, it's not that the carbide is related to activity, so that remains still this cobalt metal phase, which is suggested. Are there some questions?
There are some questions. I would invite Griffin Canning to ask their question.
Thank you. So actually, you really answered a lot of it. The question was related to the formation of carbide phases or even solid solutions of carbon in cobalt, and whether you could collect scattering results. I'm not a scattering expert, so I don't know, but can you collect scattering results with the same spatial resolution that you collected the XPS results?
Well, first we have X-ray diffraction results and X-ray absorption spectroscopy data. So we have no scattering or emission data on these systems, and also not XPS. The second thing is that when we started it, we were somehow, I would say, naive. So we thought cobalt metal is claimed in the literature. Cobalt oxide is not claimed, but can always be present, maybe in combination with support cobalt titanium. Now, what we notice is that almost every technique which we now touch sees somehow carbon and cobalt. Remember, I also showed that in the first CO2 case with nickel and carbon. So seemingly at the surface, this cobalt carbon is formed. Maybe in the beginning as this aromatic species, which I show you in the Stixon. However, later and later on, what you notice is that there is this dynamics at the surface, which leads to a kind of layer and a deeper layer. And at some point, you see the formation of something which is detectable with X-ray absorption spectroscopy. And later on by X-ray diffraction when it has sufficient structure, if I may call it that way. That's what we see. And that is how far we have pushed it. Other questions?
Yeah, I appreciate the answer. I apologize. I'm actually collecting some X-ray data right now, so attention is torn. But
thank you.
I wonder about the ability of neutrons to help you out with this, since the carbon is such a light nuclei. You know, that might be a path forward for understanding some of that chemistry.
Yes, and for this actually, I have already been thinking about it, and I was once. I've been several times, but I've been discussing it at Oak Ridge National Lab and also in the UK. In the UK, there's a group also which is active in this. And okay, if time and effort and whatever allows us to do, then I think that we will go to try to do that as well. But so far we did not try it out. So if there's a person in the audience who feels triggered or motivated, I'm always open for starting in that area something. But it's something we have thought about.
Very good. Matthew Marcus, you have a question?
There it goes. Okay, I was wondering, going back to the XAS data, the QuickSAS data on the nickel, I noticed a progressive phase shift in the spectra, and which would suggest a distance shift, and you didn't seem to say anything about that.
No. What we have been thinking is and we actually have been putting schemes where we build in the carbon in the nickel and then actually try to see if that would fit also this. Is there a way that we could, for example, do the go back and say, okay, assume this would be the structure, what would be then the spectra, and how would that then gradually change that? I think that the carbon.
I've lost your sound.
Yeah, Bert, your microphone just stopped. No, still no.
Now I've lost his video.
I have his video.
Well, he froze.
So you hear me?
Yes, now we hear you. Yes.
Seemingly my headphones does not work anymore.
You're a little faint, but you're audible.
So where were we?
Carbon and nickel.
So the nickel, the carbon. So what we suggest is that the carbon goes into the nickel phase.
Interstitial.
Interstitial. Therefore, we see the difference. And that because you do that back forth, that goes actually deeper and deeper and deeper in that nickel particle, which then really starts to form. And that is also the reason why I think that with this cobalt particle, the last thing, there I show also something of cobalt carbide, but in the beginning you don't see it in X-ray diffraction. With the XAS, you already see something. So the XAS is much more sensitive to that.
Oh yeah, speaking of cobalt, I'm surprised that you could reliably fit the difference between FCC and HCT because they're so similar.
Well, that we have been, I can, if you send me an email, we have been working, but we have been working on this already for a few PhD students, and we have been trying to make good reference, but also having it done with different techniques to double check on that. So I agree.
The commercial
so it remains subtle, that I agree.
Yeah, I get that commercial cobalt metal is a mixture.
Yeah. But you have to make many of the phases which I describe, you also have to make yourself, for example. The cobalt carbide is also not a trivial thing to make.
Mm-hmm.
Good.
Okay, you should continue, please.
Sufficiently answered?
Wait 1 second, one more question. David, you have a question?
Yeah, it's somehow related to the last question that was asked, like the distinction or between cobalt, HCP and FCC, and I was wondering if epsilon cobalt could also play a role in this, or if it could be resolved. I mean, I know it's a metastable phase, but would that add maybe or reduce the uncertainty in the end of?
I think I have to answer then also the previous question. See, what you do is you have references, then you do linear combinations, and you have your standard spectrum you should take. That also has a not perfect fit. Hence, what is the remaining part? Is it because your references are not perfect? Is there a phase missing? That is the risk and the uncertainty in all this fitting. And I don't know, see, the cobalt is still a more simple system than the iron Fischer-Tropsch system, where you have even more carbide phases possible. So there it's even more difficult. Okay.
See, thank you.
Very good. You should continue, please.
Yeah, okay. Then I want to talk about the last part. And the last part is partially published and partially unpublished, but it is because I also thought that the chairman of this series of lectures is very interested in it, and it's lab-based X-ray spectroscopy. And the focus is on active phase determination and bimetallics characterization. I want to focus on cobalt, nickel, iron, and copper. Now I took here Sabatier and Fischer-Tropsch together. Now why? Well, you can argue what is now the difference between CO2 and CO hydrogenation if you know that CO2 has one of the intermediates CO. So, and also because if you take now an iron or steel industry, often these exhaust gases or these streams, they contain not just CO2 but also CO and also some small amount of hydrogen where you have to add more. So it's important that you can do both and that you explore both. One of the techniques which I want to bring now on the table is lab-based XAS, and I feel that we should give some credit to this recent review paper, which was published in Coordination Chemistry Review, which discusses this XAS and XAS into the laboratory. Can you do that? Now, I'm not that old, but at least it's a revival of some ideas in the 80s. And you can find in this book a chapter by D. Koningsberger on this. And here I show you an old paper in the 1980s, which describes a setup. Somehow it did not pull further, but nowadays, because of very good X-ray sources and also better detectors, it's again alive and kicking. We have been working together with scientists at the University of Helsinki, in a special Simo Huatari. And for references, I show you some ESRF data which we collected in Grenoble. The setup is those developed and found. You can here find the reference, which is a Roland circle. And here you see the X-ray tube. And here you find our in situ cell, which I already described before. This in situ operando cell, you can determine what is happening. And you have a back pressure regulator, which allows you to measure high pressures. So we used again our cobalt titania catalyst, which I described before. I show you here lab-based XAS, synchrotron XAS. No doubt, synchrotron, higher signal to, or better signal to noise ratio, here more noisy, but you can record such spectrum. You can measure it at, for example, 1 bar. You can also bring it to higher bar and up to 5 bar. And here I show you different ratios of hydrogen CO for the lab-based. Clearly, you can now measure in a lab XAS under operando conditions of a catalyst. And I already showed you before this kind of plot where we have been using cobalt metal and cobalt titanate to plot and see what is happening and what is present in the catalyst. Mainly metal, some, although you see the error bars, some titania oxide, titania phase. This is the papers which we published together with, this may be interesting for the one who also asked questions about cobalt carbide, where we also have been studying in this follow-up paper, cobalt carbide formation. Now I will show you the results which are unpublished and are based on a long visit from Nina Gens at the Huatari lab in Helsinki during the COVID period. We have actually made two changes to the setup. We have a motorized sample cell stage and also motorized crystal exchanger. And with this, here you see the cell. And here is the other device, which is placed here, and also product analysis. You can now do this operando for multi-edges. First, I show you that it works catalytically. This is Fischer-Tropsch CO2 hydrogenation, my excuses, where you make methane and CO. Now what you have is the activity is the highest for nickel, then nickel iron, then nickel copper. And the methane selectivity is very high for the nickel. And then you see that these bimetallics perform less good. The whole point was not to make the best catalyst. The whole point was, can you, while you do catalysis, measure with this lab-based different edges? And that I want to show you here. This is the nickel catalyst. This is the nickel iron catalyst. Here I show you the nickel edges. And here I show you the iron edges. When you have iron around, then you see that this pink, for example, what we first do is we heat it up, reduce it, then cool down, and then do C2 hydrogenation. So two phases. You heat it up, you reduce it, and then you run the catalysis with CO2 and hydrogen. Here you see this waterfall type of these plots where you have temperature as function of the energy for nickel and the iron. What you can notice is that when you have iron around, as you see here, that it will influence the reduction. While for the iron edges, you see changes, but they are much more deconvoluted. What about the copper? The nickel copper. Here I show you the nickel. And again, the nickel reduction is affected. Here you see the spectrum at 200. You see it without, you see here. So here I saw it already from iron. See that also difference? So that you see the difference. And this is for nickel and copper, the nickel edge. And here you see the copper edge. If you now analyze that and you determine what via linear combination of the different species which may be present, and I have to make this warning because it is, of course, an assumption what you put into this fitting, then you see that you have for the nickel, mainly the nickel. But when you have copper, you see a little bit, but I would say that is still within the error. But you have huge changes in the copper and iron phase relative when you see that with the nickel. This is measured CO2 hydrogenation 400 degrees C. These data are not yet fully, I would say, digested, but I hope I've convinced you that you can now do with different edges, operando, relevant reactions, CO2 hydrogenation, and follow it with these different edges, what is happening in a bimetallic system. And that brings me to the end of my talk. I wanted to talk about XAS, microscopy, long duration experiments, and then lab-based methods. I took the CO2 CO hydrogenation as an example, and I took these elements as the catalyst. Where do you want to go? You remember I showed you a slide on catalyst filming, from birth to life to death. Actually, what you want to have a full movie of this from birth to death. You want to do that over extended time periods at different length scales. That means that actually this camera, which I showed you in the beginning, will have to be adjusted that you can zoom in, zoom out, but at the same time, during a real long period of life, follow this. For synchrotrons, That means that you will have to have regular access with your setup, or keep your setup there and put that in the beam now and then. With lab-based systems, like this lab-based XAS, this should be an X-ray diffraction machine. That should be, of course, be possible, provided you can run an experiment, for example, for months or a year. But that will be the way to really understand the activation of functional materials like catalyst. I also want to bring to your attention that we are dealing with a large set of data. That means that data mining and machine learning will become essential, and that also will have to develop. Because the speed of producing data, or at least when you want to analyze them in the way it's processing, also understanding, then at this moment, that is the rate determining step. With this, I would like to end. I'm looking forward to your questions, and I hope I've inspired some of you to conduct these operando type experiments on functional materials like catalysts, but I think similarly you can apply them to fuel cells, batteries, and so forth. Thank you.
Thank you. It was a wonderful talk. Well done. We'll start the questions off. Adam Hitchcock.
Hi, Bert. That really is a beautiful presentation, weaving together so many nice themes using X-rays. You showed a bunch of data analysis in some cases using multivariate statistical analysis, PCA and follow-ons, and then in other cases using reference spectroscopy.
Yep.
I wonder if you could just sort of say a few words about your perspective on which one's better, or in which situation it's a better approach to use one or the other.
Well, some of the questions already have been pinpointing where the problem is. Do we have good reference materials? Reference materials is an issue. And I think, as you know, with carbon materials, where you're an expert in, that reference materials are good if you know what you have in your system. And that is where often, like catalysis, but not limited to catalysis, there the issue starts. So you have to have a good idea what is in the system, and hopefully by that to do that. So that puts this, what I would call, where you, an analysis where you say, okay, I fit with 4 or 5 components. There you see, and whom, then you always, you know, everyone knows fitting an elephant. The more parameters you put into the system, the better the fit can be. So that means you will have to have cross-checking. I hope, but I'm not sure that that was really coming clear for this cobalt titanium, but we bring from different methods, different views. And we try to correlate X-ray diffraction with XAS, with STIXM and TIXM and so on. And by bringing them all together, this elephant, hopefully you can better see, feel, understand, and hence, therefore, better fit. That brings me to the first approach. There, a priori, no knowledge has to be put in. But then what is then this pure component? And then you're again confronted with the same thing. What I forgot to tell, and where I'm not an expert in, is that you can also do theoretical calculations and try to do theoretical calculations of. These things will all have to merge. But it starts always with a good knowledge, chemical knowledge, what potential phases are there. And that requires experience and expertise.
Thank you very much. I really resonate with what you're saying there. Without having a reasonable chemical guess about what you're dealing with, and then using reference spectra, you really can go off the track. And I'm a bit concerned that as we go more and more to purely statistical methods, particularly with high throughput, machine learning, artificial intelligence, that we're going to lose the contact with the reality of doing reference spectroscopy. I think the best, of course, is to do both, and of course to do multi-technique, and you've shown beautifully. how your group is doing exactly that. Thank you very much.
Thank you very much for the nice words.
All right, Jeff, you have a question.
Yeah, Bert, you showed some results, I think, early on where you sort of correlated, excuse me, the Fischer-Tropsch activity with the metallic cobalt.
Yeah.
And then you, toward the end there, where you were looking at copper with nickel and copper with cobalt, I guess, it looked like when you formed an alloy, which kind of prevents the carbide formation, that you sort of didn't have activity. Did I see that right?
It's true that with copper, it drops and drops a lot. But I must also say is that the iron case, I do not understand that well yet, because iron you would expect to be able to do that as well. Especially because what I forgot to tell and what you're aware of is that you have still also reverse water gas shift reaction going on. So that means that it's most probably a bit more complex than I described, and therefore I just want to state that I presented it as a showcase where you can measure it, but I'm not saying that we understand what is happening there.
Yeah, so I appreciate the spectroscopy for sure. I guess the question is metallic phases, if that's truly the active phase, I would think alloys, which would prevent carbide formation, should have been pretty effective, yet it didn't look like that was the case.
No, but for that, I think it's the question is, okay, the copper is also not innocent to CO2, because it's also known to do CO2 hydrogenation, but making methanol. So I'm not sure what that is there, what that effect will be.
So I guess the ultimate question is it a mixed cobalt carbide phase that becomes active versus, you know, a nickel versus nickel copper phase?
Yeah.
I mean, it's certainly super complicated.
Yeah, but I'm more optimistic that we can crack down the nickel iron and the nickel iron and nickel itself than the nickel copper I see as a not so trivial system. But it was, I think, a nice way to show what you can do and that you can measure these multiple edges. I think that is a really, I just saw also that, I think, wait, was Simo is around. So Simo, that is.
And if I might, one quick question. You know, titanium has been long at it as a promoter.
Yep.
What do you view as the critical role of titanium in making these things more effective? Do you have a thought about it?
Good. There are several oxidic, reducible oxidic supports, oxidic promoters. You bring now titanium and say titanium support, but is also a promoter. I think that is a wise words, because you can almost all of the data I show there is an interaction between titanium and this cobalt. It also holds for other reducible oxides, such as manganese. Manganese, titanium, cobalt is also known as a Fischer-Tropsch system. And every time where you can put or deposit on a cobalt somehow these reducible oxides, like titanium, there you note that it has this promoting effect, but also the possibilities to shift even the product distribution.
So do you think that's an SMSI type of promoter effect?
What is SMSI versus a reducible promoter effect?
Well, it's the oxide that moves mobile and moves onto the surface of the active phase, right?
Yeah, but the question is, what do you do when you prepare already a catalyst and you, for example, deposit already a reducible oxide on it? It's also somehow, well, it's not called SMSI then, but it are patches of a reducible oxide which is nearby the metal particle.